Hi, it's Robin. In a previous video, we took a look at this game, Livingstone, I presume, on cassette. One of my favorite games from when I was a kid, but it has a game-killing bug. About halfway through, it just crashes. Back then, I thought my pirated copy was to blame, but no, it's right on the original cassette. So last video, we figured out the cause of the crash and how to live patch the game to fix the problem. But at that time, I wasn't able to make a fixed version of the game that could just be loaded from cassette or from disk. So today we're going to try and crack this game. That means remove the protection and make it just a raw program file which can be saved to disk and just loaded and run, and also fix it so it's better than the original game. So this isn't really about piracy, it's about correcting a 35-year-old bug in a commercial game. Thanks to my patrons for this video, originally a patron exclusive, and particularly Ian Calhoun for inspiring me to actually figure out how to do this cassette tape cracking. Now, I'm no expert at this. In fact, I only just learned this recently, in large part thanks to an article written back in the 90s for Discovery magazine, issue number 3, called Defeating Digital Corrosion, aka Cracking, A Beginner's Guide to Software Archiving, which was written by Jan Lund Thompson, also known as QED, or I think Qued, Triangle. So a big thanks to him and everyone else who shares their knowledge with others. I'll put a link to that article in the video description below. Now today I want to try doing this with all original era equipment from the 80s to early 90s. My Super Snapshot freezer cartridge, a regular cassette deck, and the only exception is I'll be using my micro IEC SD card drive just because I'm running low on floppy disks now. But we won't be doing anything with it that you can't do with a regular 1541 disk drive. Okay, so I've got the C64 booted up here. We're going to use this F1 setup for snapshot function. Are you sure? Yes. All memory is going to be cleared. And all that does is clears all of RAM with the pattern hex BB. This isn't completely necessary, but it'll come in handy. It'll just make a couple things a bit easier, and I'll show you that later. Okay, we'll go to basic and put the original cassette in the cassette drive. Now, some tape games, it's just a matter of typing in load, press play on tape, and they will just load into memory, and then there will be a ready prompt where you could then just save it off to device 8, off to your disk drive. And for some games, early games, that's really all there is to it. It's that easy. But I'll just show you what happens in this game, and actually almost all cassette games published, I don't know what year, 84, 85, 86. Here we go, found Livingstone, press to load. And now instead of coming back to the ready prompt, this happens. The border starts flashing, it says Livingstone Nova Load N102604, that's apparently the serial number. This is a custom fast loader that's active on this game. And not only does it have the convenient function of speeding up the loads a lot, but it also adds some copy protection. It automatically starts the program, and there's never an opportunity to save the game or have the command prompt. So our first step is to figure out how to defeat that auto start. So I'm just going to stop that. You see how the border stops flashing when there's no more data coming in. It's just like a diagnostic tool. Okay, so I'll just reset the computer again, and we'll just start back where we were. Okay, so load doesn't work, but instead we can just do a sys 63278, and that's jumping directly into the kernel operating system. And here we'll just press play, and this routine will just load the program header into the tape buffer and then stop. Okay, here we go, found Livingstone, press Commodore, You see how it returns to the ready prompt. Now I'm going to press stop. Sometimes if I go into the super snapshot with the play button down, the tape will start running on its own, and we don't want that to happen. Okay, so here we are at a basic prompt. Now I can go into my super snapshot machine language monitor and take a look at memory, and that cassette buffer is located here at 33C in memory. And over here we can see that the file name is here, Livingstone. What we're interested in is the 5 bytes before that. This first byte at 33C is the block type. And if it's a 1 here, that means it's a relocatable program file, which is typically a basic program. That is, it doesn't have to sit in a particular location in memory. Type 3, what we have here, means that's the header for a non-relocatable program file, which is usually machine language. Then the next 2 bytes are the load address in low byte, high byte format, so that's O2A7, and the load end address, which is 10A7, 1000A7 hex. This is going to load into memory at O2A7. While a normal basic program, or actually a normal runnable program files, are loaded into memory at 0801, so this is actually being loaded really low into memory, which is where a number of basic and operating system vectors are, memory locations. That low load address is causing data to be written into low memory, and the C64 has no protection against those sort of exploits. Now, in a previous video about load star, 8, 1, I actually looked at a number of these Autostart features, which really are basically operating system exploits. That's what we would call them nowadays, but back then, of course, nobody really cared, and they were at least somewhat for our own good. We didn't have to type run, but it also was used as a form of copy protection. So we'll look at that Autostart in a bit more detail later, but the important thing to know is the reason it works is because the program is loaded to this location, O2A7. So what we can do is just add 1000 hex, that is 10 hex, to the high byte of the address, both the start and we might as well do the end address as well. And we're just adding 1000 hex to each one, that is 4096 decimal. I'm just going to press return. And so now we're going to load to 12A7. There's nothing magic about that. It's just convenient to add 1000. This seems to be best practice from the article I was reading, because it allows the low 3 nibbles of the address to remain the same, and then the high to only be off by 1. Just keeps everything kind of convenient and consistent, easy to remember. And now that we've modified the load address, that's just going to make it so the Autostart can't exploit it, because it's being loaded into regular program RAM, not on top of any operating system vectors. Okay, so we can just exit back to basic. Now there's another sys to actually execute the load. We loaded in the header block as a separate step. Normally it's all done together. We modified the block to tell it to load to a different address, and now this will complete the load. So again, press play on tape. We'll do that. There we are. Okay, back at the ready prompt, having loaded the loader. The whole program isn't loaded yet, but we've loaded initial loading program. I'll press stop again. And we still have control of the computer. No auto start. I'll go back into the monitor. And now we can look at the code. We told it to load to 12A7. And there it is. And there's about 512 bytes of it. There we go. And we can see where it ends because there's all these BBs. That's that fill byte that the super snapshot puts in if you tell it to initialize memory that way. And that just makes it really easy to see where a load begins or ends. Otherwise, the uninitialized RAM might be full of kind of garbage, zeros, Fs. It's not predictable otherwise. So we know that the last valid byte is at 14A7. So the next one is 14A8. Okay, now what we can do is transfer that memory, 12A7 to 14A8, back to where it belongs at 2A7. And now that's done, but Autostart doesn't happen because right now the machine language modder is in control. So we've loaded that program in, higher in memory, gone into the modder, and then moved it back down to where it belongs. And now we can look at it. Disassemble 2A7, and there's the code. But we don't necessarily know that this is being executed. We still have to figure out exactly what the exploit is. So the place to look at that is if we look at memory, starting at location 300, and this is where all those vectors are, and they are pairs of bytes, which form a 16-bit address pointing to a routine. And we're looking for one that has a high byte of 2, 3, or 4 in that memory range that was just loaded, where the code is. And so if you look through here, the one with a high byte, it's always the second byte, is right here at 0328 and 0329. They form a 16-bit pointer to 02ED. Okay, so 0328, if we look at mapping the C64 or other references, we'll learn that this is the kernel stop vector, and normally it points to F6ED. So it's being modified to point to 02ED. And this routine checks for the stop key being pressed, and among other places it's called while loading from cassette. After every byte is loaded from the cassette, the stop key is checked to see if the user wants to cancel the load, to stop the load. So the end effect is that all these bytes from 02A7 all the way through to here have been loaded off the cassette, and as soon as this one is overwritten, the load routine calls the stop vector, but it calls this code instead at 02ED. So let's look at that. What did it execute? 02ED. Let's disassemble that. And it's this little snippet of code, which loads an F5 and stores it in 0496, and then it stores it in 0328, which is this vector again. Now the stop vector is going to be pointing at 02F5. This actually took me a little while to figure out. At first it seemed really cryptic, but basically this F5 is being used as a flag for the end of the load process. And then it's also going to repoint the stop vector to 02F5, which is right here, just a little later. And then that 0496 is going to be checked. Branch if minus, that means if the high bit is set, then it will jump ahead, and otherwise it'll jump to 0400, which is normally screen memory, but code's being loaded there. So basically, the first time the stop vector is overwritten, it sets this flag and repoints the stop vector to this line, and then it exits, and then the loading process continues, and after every byte, it's going to be checked. Is 0496 a positive or a negative number? That is the high bit set or not? And the data on the tape will eventually overwrite this location and make this branch fail, and then this jump will go ahead to 0400. Now, because we already intercepted that load's already done, so we can actually already disassemble at 400. So here's more code that seems to set up the screen. It sets all of color RAM to color B as well as the background, so whatever text is on the screen will be invisible. And notably, here it's clearing out screen memory, but not at 0400, which is the top quarter of screen memory. It's leaving it alone because that's where this code is. So it's basically hiding the code, making it invisible. It does some other initialization here, which I haven't fully figured out. But when you're doing this kind of work, you don't have to figure out every little bit of code. Okay? And here at the end, this is what gets important. It jumps to 02A7, which is the very beginning of the code that was loaded in. So let's look at that, 02A7. Now it's done with all that code at 0400, so it actually does erase it now. And then it calls this routine at 0345. And this is a whole bunch of code. It messes with the CIA timers here. And again, we don't have to get really in deep with this, but basically this is the fast loader right here. And all the way to 3D3, quite a bit of code here, where it exits again. This is the code that loads the rest of the game. And instead of using the regular kernel tape loader routine that's built into the C64 kernel, it's a fast loader. The rest of the program's being encoded with a different protocol, and this code is what successfully can read that in. The regular kernel cannot load the rest of the tape. That beginning header and loader program, 512 bytes or so, but this fast loader has its own protocol. Cassette fast loaders, of course, don't physically speed up the tape. They don't spin the motor faster. Instead, they use a more compact, a tighter protocol that packs more information into the same amount of tape, therefore taking a shorter amount of time. Now, this is a huge subject on its own. I'd like to make a video about it someday, but not today. Again, we don't have to understand how everything works here, just that once the loading is done, it does an RTS here at 03D3. And we'll look where it goes. It goes back to here, here, and this is the important part. This is really all we've been looking for. JSR 4000 hex. We already know from last video that this is where the initialization for Livingstone is. This is very close to where the bug is in the game as well. So this is the point where the Nova Load system has loaded the entire game into memory, and it hands control off to the game, to the payload. I don't know why it uses a JSR here, if that's just for confusion, but I know that the Livingstone code actually resets the stack pointer, so it doesn't even matter that it's a jump to subroutine when it could have just been a regular jump. So this is where we want to intercept. This is what we've been working towards. So there's probably all kinds of ways we can do this. This is how I'm going to do it. 2BC. I'm going to assemble to 2BC. I'm just going to clear carry, and I'm overwriting that JSR 4000 right here. You see how it's 3 bytes long? I'm going to write 3 other instructions. 1 byte is a clear carry, and another is branch if carry is clear, which it will be, back to 2BD. So now we can look at this again. Okay, and where that JSR 4000 used to be, there's now a branch of carry clear to 2BD. It's just an infinite loop. So all we've done is prevented the game from actually running once it's done loading. It's just going to sit in an infinite loop, which, well, would be a crash, except we can use our Super Snapshot cartridge to go back into the monitor and take control of the computer again. Okay, so after we've modified that, we don't necessarily have to do this, but I'm going to boot. This is called boot 01, and we're just going to save our modifications to disk 02. So starting at 02A7 and going up to 04A8. All right, now it's saved on disk. We're going to reset the computer. Going to clear memory again. And I'm going to load boot 01, 8, 1. Hey, there. So it has auto-started just as if we load it from cassette, but we actually load it from disk, and now it's waiting. We'll press play, and now the game is going to load as before, but instead of starting the game, it should freeze and allow us to do our next step. So this will take a while. I'll just jump ahead. Okay, it's finished loading. It looks like it's crashed. but hopefully it has not. I'm going to press the freeze button. There we go. We'll go into the monitor. And yeah, that's the location where we modified it. It's just an endless loop. So now we're going to be able to save this to disk. So we're just going to look around in memory to see if there's anything weird here. Okay, video RAM just looks like it's, well, what was there on the screen. So it looks like the program's starting near the normal location. So it should be safe enough just to, like, this is just kind of garbage bytes. Actually, it looks, this prueba, I think that means test in Spanish. So, and look at that, RS-232 CBM. So did they have some sort of like a transfer program? Maybe they made this with some sort of cross-development system over RS-232? I don't know for sure. But there's just a bit of interesting stuff there. Well, that's some Spanish. Okay, so the start address 0801 should be okay. Like I said, I'm just a beginner at this, but I think even the most skilled people, there's some trial and error involved. Okay, so now the question is, where is the end address? We're going to save from 0801. That's just the standard place that Commodore 64 programs start. I don't see a reason not to. So if we interpret memory starting at, this is like the end of memory, and we're looking for those BB bytes, which will show up as little squares. Okay, so it looks like all the bottom of the code, oh, there's that prueba again. Excuse my Spanish. Okay, now we're looking at the ROMs here. So basically the program is so long that it goes through all of regular basic RAM, and it's probably gone under the ROMs here. So I'm just going to change memory location 1. I'm going to switch out the basic ROMs by changing that low nibble to a 4. I'm going to switch out all the ROMs and the I/O actually. And now again, we'll interpret starting at 8000. If I didn't make that clear, here is the CBM basic indicator. That's how I know we're looking at the ROMs there. So now I'm going to look at that same memory location. You see how it has different values here. So this is the game continuing under basic ROM. All A1000, all through B1000. So yeah, I didn't mention that earlier, but this really isn't like a science, and no instruction guide's going to show you all these details. You just have to get experience to learn. Okay, so here we are. C800 is where the program ends. It loaded right up to here. So that's going to be our end address for the save. But before we save it, let's do that little patch. If we look at the code at 4000, you can see right here, when the Nova load JSRs to 4000, it sets the interrupt disable. And right here, it resets the stack pointer by loading X with FF and transferring the X into the stack register. And here, you should watch the previous video if you haven't, but basically they put one too many NOPs, EAs, no operations, in here, and we have to restore it. I'm going to just change location 4013 and put a 20 in there to make it a JSR. And now if we just disassemble that again, they had patched one extra byte and it wrecked a few things, so we've restored that. Anyway, check the previous video for a description of that. Okay, so now the game is patched. It's simple, eh? That took me hours and hours to figure out, by the way. But it just turned out to be a single byte. Okay, so now I'm going to save that game 01, 8, from the beginning of the range 0801 to C800, the end of the range. Here we go. Work. Don't crash on me now. Okay, the saving's done. Okay, and there's our game. There's a few other files on here. Yeah, I'll get to that shortly. The important thing here is I've reset the computer. Actually, I'll even reset And I'll clear RAM just to be sure. And we will load game 01, 8, 1, and we'll see if we have successfully cracked the game and saved it to disk. Okay, ready? And we just have to type in that 4000 hex is 16384 decimal. So let's type that in ourselves. Please work. Yes. And just make sure. Okay. So we have a successful, clean crack of the game that is patched and fixed as well. Okay, but we're not quite done. There are two problems with this file still, game 01. One is the huge file size, 194 blocks, and the other problem is just that you have to SYS to start it. That's not convenient or professional or whatever. You should just be able to type run. So there is a program or what we might call a tool, software tool, that can solve both of those problems. They are called crunchers, and that's what these two files are here. There's AbCrunch. I've been experimenting with these. AbCrunch is probably better, but it's super slow, and I don't want to record that. It's just going to take forever. So I'm going to load instead ByteBonker version 1.5, which is not as good, but it's faster and it works. Okay, game 01. So we'll run it. So here we go. ByteBonker. Is it Shoter's horror tool? Okay, so we're going to call that game 01. So that's the input file. And this is going to crunch the program, make it smaller. Just like on a modern computer, zipping files generally makes them smaller. Same principles here. So we're going to call this a Livingstone fix. This is the out file. And the sys address that's going to start is 4000 hex. And the 01 value, we don't have to worry about that too much. Let's say 36 to switch out the basic ROMs. Okay, it asks us the speed. We're just going to go with the fastest speed, which is 1. Okay, and source, I'm going to press the space bar and it should start loading it. And I'll talk about while it works. So just a little bit of information about this while we're waiting. There are two tools. One is called a cruncher. That is usually an LZ algorithm-based crunch. And the others are called packers. And typically those are run-length encoding. So let's see if it's going to work. Oh, here it goes. So the cracking, the pirate groups back in the day developed these tools. Actually, some of them are amazingly complicated pieces of software, in my opinion, to be writing in 6502 assembly. But the advantage was that by crunching a file, it would use less space on your disk. So you could probably pack more games onto a disk. And of course, the files could be downloaded from a BBS quicker. They would take less room. There's all kinds of advantages to shrinking your file. I won't go into great detail about it because it's a huge topic that could have its own video. But I want to make it clear that I'm using this old ByteBonker tool just because I'm trying to use programs from the era, keep this is all authentic to the late 80s or early 90s. Nowadays, there are programs called Examizer and PU Crunch and maybe others that will do this job on a modern PC in seconds, but produce an executable C64 file. Okay, and thanks to my friends Jason, Six, and Dawkin for making suggestions about what cruncher I should use. I ended up choosing this ByteBonker. I actually had problems with other ones. They crashed or there were various issues with several others, so this is what worked. And yeah, we're waiting for that old counter to go all the way up to C000, which is the length of the file. You can see the new file size currently and how much has been saved so far. So we're approaching 2000 hex bytes saved. And by the way, a lot of times crackers would even take 2 passes. They would do an RLE pass using the Packer tool, run length encoding, that would get rid of repeating patterns. That would be like a big block of zeros, for example. Do the Packer first and then crunch it afterwards, which is this LZ-based compression. So I think in total this takes about 8 minutes to do the crunching, and this is in the fast mode, and this is a pretty fast cruncher. Some of the old crunchers could easily take an hour, especially to really pack it right down and try to squeeze every last byte out of it. All right, there we go, all C1000 hex bytes. Now the new length is 7297 hex, a savings of 4D69 hex bytes. That's probably like 19 kilobytes saving. That's really good. Okay, install target disk. Here it goes. Okay, do we want to save again? No. So I'm going to reset the computer. And let's look at that file size. We've gone from 194 blocks down to a much better 116 for the Livingstone fix. So I'm going to load that file. You might remember from the other video how I noticed how all the other versions of the game for Amstrad Spectrum MSX have codes here to get infinite lives, but the C64 version, they told you to send in an SAE. And that's actually what got me started on this whole discovery of this bug and why that infinite lives doesn't work. So here we can list. So you see that the program's now runnable. It has a sys, but what I'm also going to do is activate that cheat. And we do that by typing in run. Originally, we would have done it with load, but we've defeated the Autostart feature, so we have to do it with run instead. And then we just type in opera after on 4 bytes. So this is 1 token, 2, 3, 4. On the 5th character, you type in the word opera and press return. Let's see if it works. That's depacking, decrunching. There's the game. And now, do we have our infinite lives? I'll deliberately die. Watch the hats. It goes from 7 to 6. But once again, oh, there we go, we died. So watch the hats. Yay! So you see how it's not going down anymore? That is because the infinite lives patch is there. And activated from the command line as the authors originally intended, but then they broke it when mastering the game. Okay, so I'm really happy to have that game fixed, and I'm going to have to give it a really good play now that it should be beatable. So one thing I didn't explore was remastering this onto a new cassette, and that again would be its own topic. I know next to nothing about that, but there are some modern tools around to create tap files, which can then be turned into waves and saved on a real cassette. I have no idea how I'd go about remastering it with a fast loader on a real C64, but maybe I'll investigate that in the future. For now, just the disc version will have to do. Okay, thanks to my patrons for their support. Thank you for watching, and we'll talk to you next time.